So the two major types of bonds you should now be familiar with, um, the ionic and covalent. These should be easy to recognize if you have a periodic table. Ionic Lewis structures, is an exchanging of electrons between a metal and a nonmetal. Covalent or molecular structures are when electrons are being shared between two nonmetals. But covalent bonding is a little more complicated by that than that. We can subcategorize covalent molecules into nonpolar and polar covalent molecules. A nonpolar covalent bond is one where the two atoms share the electrons 50-50. And a polar covalent bond is where they are not sharing 50-50. Somebody is hogging. Okay, here's what this comes down to. Sharing does not necessarily mean equal sharing, right? If I share a piece of pizza with somebody, I don't have to cut it down the middle and share it 50-50. I could cut myself 3/4 of it and give somebody else a quarter, right? We don't have to share equally. So electrons are the same way. Two nonmetals forming a covalent or molecular bond, they don't have to share those two electrons 50-50. They can, that kind of utopian society where everybody shares equally, that's called a nonpolar covalent bond. But most bonds are actually polar covalent bonds where the two atoms do not share equally. Somebody hogs the electrons. How do you know if a covalent bond is going to be nonpolar or polar? How do you know if somebody is going to hog the electrons? What do you do? Well, you need to look at a table of electronegativities. Electronegativity is a 4.0 scale. So when I think of electronegativity, I think of GPA. And if electronegativity is GPA, then fluorine is the valedictorian, ladies and gentlemen. Fluorine is at the top of its class. Okay, fluorine has got a 4.0. Nobody wants electrons like fluorine. And as you move away from fluorine, both to the left and down, the electronegativity values drop off quite a bit. Okay, especially you get over here. Oops. Especially when you go over here to the metals. Metals don't, so electronegativity is how much an atom wants electrons, right? Well, metals don't want electrons. Metals want to get rid of. Metals give away. So it shouldn't be surprising that the metals have very low electronegativities and the nonmetals have very higher electronegativities, okay? So fluorine is top dog. And what we can do is we can determine if a bond is going to be polar or nonpolar by comparing the electronegativities of the two atoms. And if the electronegativities of the two atoms are great enough, if the difference between the electronegativities of the two atoms are great enough, then you'll have yourself a polar covalent bond. So what are the cutoffs? Great question. Come on. Let me skip ahead here. Here's our cutoffs. If the two atoms have a difference in electronegativity of below 0.5, I like to use 0.5 as my cutoff. So if you're below 0.5, we're going to say that you're a nonpolar covalent bond. So if the two atoms are sharing their electrons, okay, and their difference between their electronegativities is less than 0.5, then we're going to classify them as nonpolar. If the difference between the two atoms' electronegativities is greater than 0.5 and less than 2.0, so if it's between 0.5 and 2.0, then we're going to say they are unequally sharing. Somebody's going to be hogging. We're going to call it a polar covalent molecule. And if the difference in electronegativities between the two atoms is greater than 2, it's probably an ionic and the electron is being exchanged or transferred. So let's go back and look at some examples of nonpolar and polar covalent bonds. So let's look at the typical polar. Here is a very classic polar covalent bond. If we look at the bond between HF in HF, hydrogen and fluorine are sharing 2 electrons, but they are definitely not sharing them equally. Fluorine is going to hog them. Here's why. If we look up the electronegativities, fluorine is a 4.0 and hydrogen is a 2.1. That is a difference in electronegativity of 0.9. That's a difference of 0.9. So, I'm sorry, that's a difference of 1.9. 1.9. So that is a very polar bond. In fact, if the difference in electronegativity was 2, we would call it ionic. So this is like as polar as a covalent bond can get. What does that mean? That means that hydrogen and fluorine are supposed to be sharing 2 electrons. But what's really happening is the fluorine is hogging them. Like those electrons are spending 95% of their time on fluorine. And then they only go visit hydrogen like on the weekend. And then they spend the whole week with fluorine, and then they go and they visit hydrogen on the weekend. And they spend the whole week with fluorine. And then they go to, you know what I mean? So what ends up happening is the electron density on the fluorine is huge, and hydrogen is being deprived of the electrons. So the electron density on the hydrogen is very small because hydrogen has the smaller electronegativity. What's that going to do? Excuse me. That's going to cause partial charges to build up. Think about it. If negative particles are hanging out on you more than they're supposed to be, then you are going to start to develop a partial charge. And we use a Greek letter delta and write a minus to represent that. That Greek letter means partial. We'll write that on the board in a minute. And then if you are being deprived of the electrons, hydrogen would like the electrons 50% of the time. Now it's only getting them maybe 10% of the time. So it's being deprived of the negative particles it needs. This atom is going to start to develop a partial positive charge, okay? So let me show that on the board. So hydrogen and fluorine are supposed to be sharing these electrons 50-50. But what ends up happening is fluorine hogs them. Hydrogen barely gets them at all. So the negative particles are hanging out in fluorine more than they should. Fluorine is going to develop a partial negative. So this is our symbol for partial. It is the lowercase Greek letter delta, and lowercase Greek letter delta means partial. So how did I make that? It's like that. It's like I'm not a musician. I don't know if that's a quarter note or half note or whatever. If you're a musician, it kind of reminds me of that. So the hydrogen is being deprived of the electrons. That's going to get a delta plus charge because it's being deprived. If I pop that table of electronegativities up here, you should be able to kind of figure this out. If we have a carbon to chlorine bond, if I pop the electronegativity values up here, come on. Uh-oh. Take a look at carbon's electronegativity. Take a look at chlorine's electronegativity. Tell me, where would the polarity come from? Like, who would be the partial positive? Who would be the partial negative in that relationship? All right. So carbon has an electronegativity of 2.5, chlorine 3.0. Chlorine, that's a difference of 0.5. Chlorine is hogging the electrons, carbon's being deprived. The chlorine will have a delta minus, the carbon will have a delta plus. Let's do another one. Let's do, oh man, I don't know. Why don't we do chlorine to silicon bond? Go ahead, put the delta plus and delta minus on that. I'm going to pop the electronegativity values back up here. Okay. So hopefully you found fluorine to be a 3.0 and silicon to be a 1.8. Oops. That's a difference of 1.2. That's definitely polar. That's between 0.5 and 2.0, 1.2. Chlorine is going to hog the electrons. It's got a higher electronegativity, delta minus on the chlorine. Silicon's deprived, delta plus on the silicon. So yeah, there we go. We got our polarity. Well, what if the two atoms do not have a large difference in electronegativity? Well, sometimes you don't even need an electronegativity table. So for example, anytime the same atom is bound to itself, so how about Br2? Go ahead, draw the Lewis structure for Br2. That's 14 total electrons. Bromine to bromine leaves you with 12. 2, 4, 6, 8, 10, 12. There we go. You do not need a table of electronegativities to determine the polarity of this molecule. Here's why. Two bromines bound to each other, they're going to have the same electronegativity. We don't have to look it up. Whatever the electronegativity of this bromine is the same as the electronegativity of that bromine. They have to share these electrons 50-50. Because these are the same atom, it has to be a nonpolar bond. There is no delta plus or delta minus. There is no unequal sharing, so there's no partial positive, partial negative. This is a nonpolar, it's a purely utopian 50-50 sharing, right, of these electrons. Now, you don't have to have two of the same atom. Now, the only molecule, the only bond that's not between the two identical atoms that I want you to memorize that's nonpolar is the C to H bond. I want you to memorize this bond. It's a very important bond. So it's the C to H bond, and we call it the hydrocarbon bond. Hydrocarbon bond. I'm going to flash the electronegativities up here. I want you to write them down for carbon and for hydrogen. Go ahead. Take a second to find them. Hydrogen really belongs above carbon for this table of electronegativities. There's no good place for hydrogen and helium on the periodic table. When you look at hydrogen, you can see it doesn't really belong here. It really belongs over here. Okay, so hydrogen 2.1, carbon 2.5. 2.1, 2.5. Now that is a difference. The difference between those is 0.4. There's a difference of 0.4. That's less than 0.5. 0.5 is our cutoff for polar. So this is a non-polar bond. What does that mean? We say that the carbon and hydrogen are essentially sharing those electrons 50-50. Is carbon maybe hogging them a little bit? Maybe a little. Maybe this is like a 55-45 kind of situation, but it's not enough to have a delta plus or delta minus. We consider this bond to be non-polar. Non-polar. So I want you to memorize that one. When you see the C to H, K stuff, that's non-polar. A lot of organic molecules, long chains of carbons and hydrogens. Those are non-polar molecules as they contain a whole bunch of non-polar bonds. Awesome. We can represent the polarity of a bond using a dipole moment arrow. Dipole moment arrow is like a normal arrow, but you make the tail look like a plus sign, and it points towards the more electronegative element. So, for example, in H to F, the dipole moment arrow points towards the 4-fluorine, and you make the tail look like a plus sign because that's where the delta plus is going to be. Now, when we get into molecular polarity, we'll talk about how to use dipole moment arrows for molecules. So, for example, water, we're going to talk about water very soon. Water has a bent molecular geometry. Okay, so the oxygen hogs the electrons. Oxygen has an electronegativity of 3.5. Hydrogen has an electronegativity of 2.1. So hydrogen is being deprived. So here's the problem. If you could draw more than one dipole moment arrow, you would probably draw this, right? It would probably look like that. But the problem is you can only draw one dipole moment arrow to represent the polarity of a molecule. So the true dipole moment arrow goes up the gut like that. So it's kind of like if you've taken physics. If you take physics, kind of like vectors, right? So this is splitting the oxygen in half, going right up through the middle like that. And that's our dipole moment arrow for water. Why is polarity important? Well, because polarity means everything when it comes to solubility. So like dissolves like, really important phrase, for solubility. What does that mean? Well, that means polar things like to dissolve in polar solvents, and non-polar things like to dissolve in non-polar solvents, but polar and non-polar do not mix. For example, water, very polar. We just looked at it. I showed you the dipole moment arrow for water right up through the gut. Oil, non-polar. This is not a why. It's a bunch of hydrocarbons. We just said that the hydrocarbon bond is non-polar. The hydrocarbon bond between carbon and hydrogen, since they have such similar electronegativities, is non-polar. This is why oil and water do not mix. They have opposite polarities.